My talk tonight is going to be about how we can manipulate neural function by neural implants. And so I hope to give some examples that start out a little bit easier maybe, and then range into things that are a little more complex, talk about where we're at with technology now, as well as where it's going to be in the future, or some predictions. So to start off, we might as well define what a neural implant is. And so if you believe Wikipedia is a valid source, then a neural implant can be defined as a technological device that connects directly to a biological subject's brain or neurons. So let's start out with something a little bit easier, I guess. So the basic senses, which I'm sure everyone's familiar with. So these are targets for various neural implants right now. And one of the more prevalent technologies that we have currently is a cochlear implant. So that traditionally consists of some external components such as the processor and the microphone, and then the internal component that's actually connected to the cochlea. And so in the future, we're looking at some changes. So in the picture on the right, we have our traditional cochlear implant, and then on the left is the newer one that's being developed right now, which is called a Tiki, which is kind of cute, but it's a totally implantable cochlear implant. So you'll notice right away that it's smaller than the other one, but the most important part about this is that it contains the microphone and the processor inside that one component. So this is entirely internal, so that would be underneath the scalp. And so I guess problems associated with that is, of course, it's less sensitive because if the microphone is not exposed outside, you're going to have more trouble picking up the signal. And it's also more difficult to repair. So if you think of if something goes wrong, you're going to have to undergo surgery just in order to access this, never mind bringing someone in to repair it on site, as opposed to if you have the external component, if you can just take it off and submit that to be fixed. And so they're trying to deal with this right now by making more durable materials to build them with, but they also have, if it's just the microphone that's broken, for instance, you have an optional external component that works very similarly to the way that we're doing it now. So there are some options, but it definitely needs some work, and there's a direction to go in the future. And so now, if we talk about vision, this is the Argus 2, which is a device that just got FDA approval within the last month in the United States. So it's been in Europe for a little bit longer, I'm not exactly sure when, but just recently brought to the United States. So for $100,000 right now we can purchase this. And the schematic kind of shows the placement around the eye, and also that electrode array is inside the eye. So it's pretty invasive if you think about placing this electrode array on the back of your eyeball, essentially. And so that's not all that's to this system. It's quite fashionable. As you can see, you've got a camera, glasses, an external processor. There's just a lot going on, and I feel like we could do better. And so, in fact, the Alpha IMS is a new system that came out just last week, actually. It was published. And so you can probably tell from the pictures already that it's quite different from the previous technology.
I have heard that you had looked at your friend Miriam, and you had seen her face. So can you describe what the experience was, the visual experience when you looked at her?
Okay, when I looked at her, I saw her mouth. It was when we started, it wasn't a little bit where the edges of her mouth were a little bit down. But I asked her to laugh, yes. And I saw the difference between laughing and a little bit down. Yeah. And then I asked her to open her mouth, and then I saw her teeth.
So you saw individual teeth, or was it a row or wide row?
It was no. It was. I saw clearly the shadow parts between the teeth.
Mm-hmm. Ah, I see. Okay.
So and then I looked at her nose, and it was light. There was light upon her nose, a tube light in the hotel room, was it? Yeah. And then I saw the shadow part. Making the edge like this on her nose. Mm-hmm. Afterwards I looked at her eyes, and there was still a little bit difficult, but I saw the shadow in her eye. There came some shadow parts in her eye. How do you call this in English?
Yeah, no, it's you mean from the light, the shadow on the lower part of the cheekbone, you mean?
Yeah, yes.
Okay.
And then, but the eye itself, there was still a little bit difficult. I thought I saw a twinkle, but that could be a fantasy.
Did you ask her whether she was twinkling?
I know she was, but
No, she was, okay.
she was just just as excited as I was.
Yeah, I can imagine.
So anyways, improvements of this technology versus the previous one, and really they're not that far off from each other in terms of time. Like this is only within the last year or so that these have been developed and tested. And so some of the improvements, of course, you could see with that video, less external equipment. So he didn't have the glasses, he didn't have the external processing unit, none of that. There's 1,500 electrodes in this unit compared to the previous electrode array, which only had 60. So if you convert electrodes to pixels, we're talking about 25 times more pixels in this than the previous one, so that contributes to a lot of the resolution, obviously. And so you can see if he can differentiate teeth with this one, the previous one with 25 times less pixels is probably going to pick up far less. Vision is based on eye movement, so both of them have a fairly narrow scope in terms of visual field, but the previous one with the camera, that's where the input was coming from, so you would have to turn your entire head in order to change the visual field, whereas this one is more natural, it's based on eye movement. This one's wirelessly powered, and then an additional bonus is that you've got some brightness adjustments. You're able to dictate that depending on your lighting environment or personal preference. So what about new senses? So we're kind of moving away from our traditional view of the 5 basic senses. So this is something that a group at Duke University, I believe, has done with mice so far. They fit the mice with a little IR detector cap, and that's attached to stimulating electrodes, and that allows the mice to actually perceive infrared light. And so we're not sure if that's a new sensory modality or not, because of course we can't just ask the mouse how it perceives this new stimulus, but it's definitely a gain of function. So we'll cross our fingers that maybe we have a video. So I guess I should warn you ahead of time, there's a really annoying noise, but it's supposed to reflect the neural firing. So you can see hopefully how the mouse interacts with the different ports and how it finds its way around using infrared light. He's already kind of guessing about that one. So anyways, he's using that, if you can tell from the sound, he's using that every time his head passes through, it changes the intensity, so he's able to guide his way, because this is invisible to the eyes. So that's not something that he's using a visual input for, that's definitely a new function. So now let's take a step further away from sensory and kind of into movement instead. So brain-machine interfaces are something that's been receiving a lot of attention lately. This picture I think was from December, where this woman is actually controlling a robotic arm and allowing her to take a drink from it. And that's without moving her arms, that's only using activity in the motor cortex. And so her neural activity is guiding the motion of the robotic arm. And the problem that I see with this is that it's movement, but it's not sensation. And so for paraplegics, for instance, you've lost movement and sensation, so this is only really fixing half of the problem. And so why that's important is that if I were to do the same task and go to pick up a water bottle, as I do so, I'm able to tell information such as, is it hot or cold, and that will influence whether I take a big gulp of it or not, as well as if it's close to empty or close to being full, so I can monitor the force. So this allows me to have more refined movement and use that sensory feedback in my motion. So to kind of go past this, now you add brain-machine-brain interfaces, which just adds another layer back. So you have the same virtual robotic movement, but now you're getting some sensation back. So this video is from the researcher's website, and it's probably better at explaining it than I am, so we'll try that one.
Using just his brain while his real arms rest, a male monkey directs the virtual or avatar arm you see here to press a button to begin an actual trial at Duke University Medical Center. Once the trial begins, 3 identical objects pop up. The goal of each trial is for the monkey to select a particular object based on its programmed texture, which separates it from the other 2 objects. The monkey's motor neurons in his brain work to move move the virtual arm. At the same time, the monkey's sensory neurons receive the texture information so he can choose the right object. The monkey uses his brain to direct the avatar arm to explore the objects until he senses the right one. This movie shows a series of explorations, each one ending with the monkey selecting the correct object. The textures were sensed as a strong vibration, a weaker vibration, or no detectable vibration. Further studies are underway. Someday in the near future, Duke scientists hope to implant a brain chip in people with spinal cord injuries so they can again experience walking, touching, and overall living richer lives.
Alrighty, so this researcher is actually working on a big project right now at the FIFA 2014 Cup. He's actually planning on unveiling a complete exoskeleton that has sensation and movement. So that'll be interesting to see if that happens on time or not, but that's kind of where it's headed. Maybe, there we go. So to kind of cap off the sensory part of my presentation, I'll just say a quick word about the IBM 5 and 5 prediction. So this was made in December, just a few months ago. And so basically the 5 and 5 is the 5 big technological advances that are going to occur within the next 5 years. And so you'll notice that this time around it was the 5 senses that are going to be, they predict are going to be replicated electronically. And I think that this is important because if we can replicate it, that implies that our level of understanding about how these processes work or how they work is reaching a level where we're able to make something that's fairly similar to the way that it works in our body. And so if we can do that, then I think we can feed that back into enhancement if we need to enhance one of the senses or repair it or something like that. So if we start getting more complex now and talking about cognitive functions, so this is a project, REMIND. It stands for Restorative Encoding Memory Integration Neural Device. And so this is a project that was going on to try and see if we can influence long-term memory formation. And so what they did was they had electrodes implanted in the hippocampus, which is involved in long-term memory. And then they recorded activity during long-term memory tasks. And after that, they tried to go back and stimulate those neurons in the exact same way or in a very similar way as what was naturally recorded. And what they found is they actually understand more about the memory encoding process now and the patterns of activity that are required. So that's feeding back into our knowledge base. But also, they did find substantial enhancement of memory function when they went back and stimulated it. So their performance, it was a mouse in this case, the mouse's performance on the same task or on similar tasks was enhanced after stimulating those neurons in the same way. And so they've moved on to non-human primate testing, so it's fairly close to human use. And this would be important if you're considering stroke patients or someone who's had damage to that area of the brain and they're having trouble developing long-term memory. So you can see the impact that this would have on someone's life if we're able to restore that function again. And so another area of the brain that's undergoing extensive research at the moment is the prefrontal cortex. So that's the area of the brain that's thought to be very responsible for decision-making, planning, working memory, problem-solving, those kind of things. The things that we label as executive function. So it's extensive in primates, the prefrontal cortex is, but especially so in humans. And so this was a study. It was conducted in a lot of the same ways as the previous one, of recording activity and then trying to replicate that same pattern of activity again and seeing how that influences the performance on a task. So the only difference in this case is that a different area of the brain, a different task that's supposed to tap into executive function instead of memory. And so the results are pretty interesting. If we look at the graph on the top right, on your y-axis you've got % correct, so that can be your performance in the task, and then on the right it's increasing difficulty level. So if we take the blue line as our reference, as a control point, the yellow line is the performance after there's been stimulation to that area. So you'll notice that it is higher across all levels of difficulty. And then the other condition that they introduced in this study, which I thought was interesting, was the presence or absence of a drug. And so the drug that they used was actually cocaine. So the red line there is showing what happens when you infuse cocaine into the prefrontal cortex neurons. You'll see the performance drop significantly. But I think the most interesting result is the green line, which is the presence of cocaine, but also the presence of stimulation. So you'll notice that it's really close to the yellow line pretty much all the way across. I don't know if it's statistically significantly different. And so that's significant because it shows that not only can we increase the baseline of someone with normal functioning, or in this case a monkey with normal functioning, but we can also, if it's impaired, raise it to a fairly comparable level. And so to summarize the cognitive functions, it's important to realize that humans are beyond simple input-output in terms of the way our brain works, so we're very different from a remote control. We have internal events that happen in between the sensory input and the motor output phase of how we interact with our environment. So these are things like interpretations, memories, and comparisons. And so we can look at a scene, see if we recognize it. Is it similar to something else? Can we build links between things? And so the take-home point, I guess, is that our experiences are complex and we're just starting to understand these processes. So although we're making gains in things like memory enhancement and even executive function, which are getting more complex, intelligence, for example, is a very broad case that incorporates a lot of smaller functions. So with that being said, I think we should take a look into what might come in the future. And so some things that I noticed were nanowire electrodes. So these are smaller than conventional electrodes and for that reason are going to be less likely to cause damage to the neurons that you're actually injecting or inserting the electrodes into. And then furthermore, I guess that they're non-irritable to the surrounding neurons, which is important if you're thinking of making a neural implant that's going to be in place for a long period of time. You wouldn't want it to cause irritation or inflammation of the surrounding areas. And then in the future, they're looking at further specialization. So this is something that's in the planning stages. They're looking at, can we influence specific proteins or specific organelles within the cell instead of just the cell body versus the axon of the neuron. So I think that's really exciting because you're just building on complexity and how much you can control. Another development that happened at MIT just recently was self-sufficient power cells. So most of these cells have to be externally powered in some way, whether wirelessly or with wires. But if you could get something to run off the same fuel as the brain, that would be beneficial. And so that's what they've done, is they've actually developed a power cell that can run off of glucose, which is the main fuel in the brain. And so in the future, the problem here is that they only have enough power right now to stimulate a few nerve cells, which really is not big enough for what the future is going to hold for neural implants. So the main focus is how can they harness more energy to create more power in order to have more extensive neural implants, more cells, maybe longer distance. And so implant technology needs to keep moving forward. So just because we have all of these really exciting developments, it doesn't mean that we're close to being finished. So there's a lot of fine-tuning that needs to go on, such as the magnitude. So even if we can find a way to increase our intelligence, how much is that going to be by? Is it going to be by 1 IQ point, by 5, or do you think we can do better than that? The complexity, so something like intelligence is extremely complex, as I've said. It's got multiple components. So are we going to be able to increase all of those with just one neural implant, or are we going to need to go in and modify different functions with different neural implants? Is it going to be way too complex, or are we going to be able to streamline that? And at the same time, are we going to be able to have specificity, which is more along the lines of personalization? So if someone has, for instance, ADHD, are we going to be able to put in a neural implant and cater that to their needs and be able to increase attention more so than your generic intelligence neural implant? So those are all things to think about in the future. And so I'd like to end things off by talking a little bit about money. And so if we can relate money and the funding for these projects with the amount of interest that they have, these are kind of the three big projects that I've noticed are going on right now. So your IBM Synapse project, just one phase of this actually has already received $21 million in funding. And then the Human Brain Project in Europe just received 1 billion euros in funding. And then Obama's Brain Activity Map project is expected to cost more than $3 billion. And so with these high dollar studies, large scale studies, along with all of the smaller scale ones that are still ongoing, I think we're going to gain a lot of information in the next 5 to 10 years, and we'll be able to push this technology forward. So I guess the question that we're left with is how far can we go with this? And I don't know if anyone really has a clear answer and where the limit is going to lie or how we can determine that. So I'm afraid that I don't have a good answer to that, but I'll leave you with that to think about. So if there's any questions, I can try and answer them as best as I can.
So today, this field seems to be primarily geared towards fixing or replacing what people have lost. But is there anything close to enhancement yet? How close are we to enhancement, or is there something on the market today that could be considered enhancement?
I think you're right, like in terms of trying to fix problems that maybe we already have instead of preventing or trying to increase that baseline. That seems to be where the funding is coming in, because if we think of like an aging population as well as the eradication of diseases, that's where a lot of the push is to eliminate that financial burden. So I think that's where a lot of the funding focus is, and that's obviously pushing the research forward. But as in that other study that was implying that stimulation can increase your baseline functioning, I think that's promising and gives reasons to pursue that further. So I think it's there, it's just the funding isn't directed in that field yet.
From a security standpoint, is it possible that these things, like these neural implants, could be hacked into?
Yeah, I think that's one of the main concerns about this, because of course it's nice to talk about how exciting it would be if we can increase our intelligence and such, but depending on how the implants influence us, like if it's just changing stimulation or decreasing excessive activity, I don't think we're faced with that much of a problem. But if it starts to get into the realm where it hasn't yet of actually implanting programs or implanting memories or things like that, then I think you would have to worry about that a lot more. So that's definitely a concern that would have to be regulated.
Thanks.
This is a comment/question. I was just curious about the neural implants because the theme of the presentation was that the implants were stimulating the neurons to improve activity, correct? But the goal was to help restore function for, say, stroke patients. But I feel like this technology has a limitation in that you're using it to stimulate neurons. But what if in the case of there was an extensive stroke and there's tissue damage and cell death, and in human brains this would result in scar tissue, so these neurons would be dead. So do you think that there's a limitation towards rescuing that type of damage, that extensive damage in the brain from this technology? Because from my understanding, it's stimulating what's there and using the current resources, or will the neuroplasticity of what's left in the brain be able to compensate for that scar tissue?
Yeah, so I think that's a really good point. That's something that I would have talked about if I had more time, but I was struggling to keep this under 30 minutes as it is. But the neuroplasticity is definitely a big field. And so I think you're right. If there's an extensive stroke, for instance, and an entire area is wiped out, you're not really left with a lot of options unless you can generate new neurons, which is obviously, of course, another field of research. So that's an option too. But I think there's a lot of combination of implants now and putting them into the brain and encasing them in neurotrophins. So that's encouraging the remaining neurons to grow into that area of like scar tissue, like you mentioned, as well as for adjacent neurons to just expand and be active. And so those are kind of the things that we're looking into, is the plasticity, taking over a function from the surroundings as much as we can. But I think you're right, there is going to be some sort of limitation depending on the extent of the damage, and we might have to look into things like generating new neurons and then dealing with those after they've been generated.
I just have a couple of comments actually, rather than questions. But actually, firstly, just to answer your scar question, your scar comment, there are cases, mostly in children of developmental ages, where a child has had a hemispherectomy and has actually been able to develop motor control of the other side of the body. So there are ways of creating stimulation, at least at the developmental level. So, that might be an area of research to go down. And secondly, I just thought it was interesting that you commented on the you mentioned the cochlear implant rather. And I just thought it might be interesting if that's a field that you're interested in, to draw parallels with pacemakers, because they've been under development for the last 30 years. The first pacemaker was installed in 1974 or 76 or something like that. And that was a car battery that was running that. And then, within a couple of years, they were implantable under the skin. And with my work in pacemakers, very rarely a very small percentage of them actually malfunction and require any sort of... in fact, you're more likely to have a pocket infection than you are to have a pacemaker that malfunctions. So there just might be something worth at least relating to, if this is an area that you're interested in.
Yeah, and to just kind of like elaborate on that aging point, that's definitely a good point too, is when this damage or supposed damage is going to occur. Because of course with the hemispherectomy, you're right, if that happens in someone who's say under 5, you're going to have a very different outcome from a person who's 25 and undergoes the same procedure. So you're going to have to consider that as well.
Any other questions? Thank you very, very much. That was really great.